Hi all, welcome to iitiansgateclasses once again. So, in the previous lecture, we talked more about the introduction to the algorithm and some analysis part, like on a given code snippet, how can you identify the time complexity for that code snippet, whether it's for loop, nested for loops, or three-level, four-level nested for loops, or we have some in for loops, we have some power to the iterating variable. Like if we are iterating the I variable from 1 to n, and we do I equal to I square, or we do I equal to 2 multiplied by I. Okay, so for all those things, for all those code snippets, we calculate the time complexity. If you didn't understand, you can go through that lecture again, and later on, you can analyze that part also more clearly. Okay, and you can practice more on the previous like gate questions or PSU questions, so it will clarify you better. So more I already covered most of the part. Okay, like very complex nested loops also I have covered. So in any of the exam, they won't ask you more complex than these questions. Okay, so today my topic would be asymptotic notation, and if time allows me, I will also cover recursion part. So before going into divide and conquer types of algorithm, we must know what recursion is. Okay, so that in the divide and conquer problems, which belongs the problem statement which belongs to divide and conquer, we can apply the recursion and solve the solution and get the solution. Okay, so asymptotic notations, these are the notations used for calculating or identifying time complexity. So based on some mathematical function, we will be defining those notations, and these are quite easy. So if you see, there are three types of asymptotic notation. Mainly, there are two more types, but those are not like mainstream asymptotic notation. Mostly, we denote time complexity in form of this. So in the previous lecture, I have used all kind of notation in big O format, big O notation. Okay. So there are two more, omega notation and theta notation. So let's start with big O. What is big O? So for example, there are two functions, like you can denote them Fn. So it's a function on input n. So n is a variable. And if we say Fn equal to big O of Gn, what does it mean? Okay, what does it mean? So we must know something like there must be some relation between Fn and Gn, which leads to this relation, this big O relation. So it means that at a given value for all n, that n is greater than equal to n0. Okay, n0 means after this value, this relation is applied for all. For all means for all value of n, where n is greater than equal to n0. If Fn is less than equal to Cgn, where n0 and c are constants. Okay, these two are constant. So if this is the relation, Fn is less than equal to Cgn, if this is the relation, then we can say that Fn equal to order of Gn. I will also show you some examples, not in only terms of mathematical function, but with some polynomial or logarithmic equation also, expressions, so that it will be clear. Okay. So this is how these things are for. So this is the definition of big O notation. And in the graph format, if you see, so we have one function which is basically Fn, which goes something like this. Okay, and there is one function. It could be any function, right? It could be any function. The shape does not require it goes like this. I'm just assuming that shape is like this. And we also have Gn, and we multiplied Gn with a constant c. Okay, so Cgn will go like this. This is C dot Gn. This is Fn. Okay. As you can see, up to this value, what happened that up to this value from 0 to n0, what happened that Fn was greater or maybe smaller also at some points. But after n0, Fn is less than Cgn. Okay, so this condition is satisfied. So you can say Fn equal to order of Gn. Order of Gn or big O of Gn. Okay, now let's take some example. So if we say Fn equal to n plus 10, okay, we denote Fn as n plus 10 and Gn as n. Okay, so if we take C like any value like 2, for example, let's take C to 2, right? So after a certain value, n plus 10 will be less than equal to 2n after a certain value. You can identify that value, n0, you can identify, right? But this will hold after a certain value. This will hold. So you can say that Fn equal to order of Gn or big O of Gn. Right. Now let's take one more example. Suppose Fn equal to n and Gn is equal to n square. Right. We can take C equal to 1. For each value of n from 0, n0 can be here 0. After 0, for each value of n, Fn will be strictly less than, we also denote equal to, but it will be strictly less than Gn or Cgn, where C is 1. So this will also hold. Right. Now let's take more examples here. So if we take like Fn equal to n square plus n plus 1, Gn equal to n square. Now, will it hold? Fn equal to order of Gn. Is it true? True or false? Pause the video and think about it. Okay. Now, if you see here, this is true actually. Right? This is true actually. So if you put C equal to 2, it will be n square plus n plus 1 less than equal to 2 multiplied by n square. And 2n square can be written as n square plus n square. Okay. Okay. So n square plus n plus 1 is less than equal to n square plus n square. This can hold, right? If you put C equal to 2. After a certain value of n0, this will hold. So this is true. This is true. So I'm getting my point. Like, if we can denote these things in form of Fn less than equal to C dot Gn, then this is true. Similarly, in case of omega notation, what happens? That Fn, if we say Fn equal to omega of Gn, it means that Fn will always be greater than equal to Cg, and there exists a constant C for all value of n such that n is greater than equal to n0. Here n0 and C are constants. If Fn is greater than equal to Gn, Cgn, then we can say that Fn equal to omega of Gn. Okay. In lame language, you can say that Fn will always be greater than Gn or equal to Gn. Okay. will always be greater than or equal to Gn. So for that, the graph goes like this. Here, the Fn can be like this, and this is Fn. Now let's talk about Cgn. Cgn will go like this. So after this point, n0, Cgn is less than Fn. So Fn will always be greater or equal to Cgn. Okay, so what if we say that Fn equal to n square and Gn is also equal to n square? Which one is true? Fn equal to order of Gn, Fn equal to omega of Gn. Which one is true? Pause the video and think about it. Right now, both of these conditions are true. This is also true, this is also true. How come? In case of order, there is one condition that Fn must be less than equal to. So this equal to satisfies this condition, Cgn. You can put C equal to 1 here, and this equal to will also satisfy. This is less than or equal to, right? Similarly, for omega, Fn is greater than equal to Cgn. In this case, where both of them are n square or same value, this equal to will hold, right? Okay. Now there are two more functions. Before going to theta notation, let me give you two more notation, which is small o, which is notated as small o, and small omega, which is notated as w, small w. Okay, so this is small omega. Here, this is big O only, except equal to part. Similarly, this is omega only, except equal part. So if we write small o, we will say that if we say that Fn equal to small o of Gn, then Fn should strictly less than Cgn. There is no equal to here. Similarly, in case of small o, if we say that Fn equal to omega of Gn, it means that Fn should be strictly greater than Cgn. Okay. So if both functions, if Fn is also equal to n square and Gn is also equal to n square, or you can say n or log n, both are same, both have same value, same function value, same expression, then what happens? This won't hold. Small o won't hold and small omega won't hold, because there is no equal to here. It's strictly less or strictly greater. Okay. So these two are small o and small omega notation. Now, what is theta notation? The last one is theta notation. Theta notation, sorry. Theta notation means that if we say that Fn equal to theta of Gn, here both of these conditions should hold. There should exist two constants C1 and C2 such that Fn is less than equal to C1 Gn. Okay, so this is for big O, and Fn should be greater than equal to C2 Gn, and this one is for omega. So if both of these conditions, not single, it's like there's an condition between them, not or condition. If both of these satisfied, then we can say that Fn equal to theta of Gn. Okay, let's take an example. For example, if Fn equal to n square plus n plus 1 and Gn equal to n square. Okay, so here the theta will satisfy or not? Theta will satisfy. So we have seen that if we take C1 equal to 2, Fn equal to big O of Gn will hold, which is same as this one, right? If we take C1 as 2, Fn less than equal to C1 Gn will hold here. So this first one is satisfied. If we take C2 as 1, then Fn greater than equal to C2 Gn will hold. Okay, if we take C2 as 1. Right? So both of these conditions will hold. And for a given example like this, the theta notation is satisfied. We can say that Fn equal to theta of Gn. Okay, now let's take few more examples. If you want to check the graph will look like this. This is Fn. Okay, and let me draw. The other one is green. This is C1 Gn. This is Fn, and this is C2 Gn. Okay, this is C2 Gn. The graph will look like this. Here, Fn equal to theta of Gn. Okay, so that is done. Now let's take some example and try to identify which one is true. So if we say that n cube, Fn is n cube here, equal to omega of n. Is it true? Yes. This is Fn, this is Gn. N cube is greater than n. Okay, n cube is greater than n. So you don't have to worry. This is already satisfied. If we say that n cube equal to omega of n cube is equal to omega of n square, n cube is greater than n square. This is also satisfied. If we say n cube is omega of n cube, okay, the equal to part is satisfying here. If you say that n cube equal to omega of n raised to power 4, no. For any constant, there could be a value of n, because we are considering that n is a variable. We can increase the value of n as much as we want. There won't be a value of constant. There won't be any value of constant. If you put any value here of constant, I can increase the value of n significantly such that this condition won't hold. So this is not true. Okay. Now let's take an example. So is it true? Like this is true here, but n cube equal to small omega n cube. Is it true? No, it's not true, because the equal to condition is not satisfied. Here we say that Fn is should be strictly greater than Cgn. Equal to is absent. So that's why it is true if both functions are same. It is true for omega, big O, but it's not true for small o for small omega. Okay. Now let's take some examples here. Okay. So we have something like n raised to power 4. Let me write it in another color. N raised to power 4 multiply dot means multiply 32 log 2 n equal to theta of n raised to power 9. Okay, so basically we have to solve this one. It says that we have to identify if this is true or false. If it's true or false. So remember this logarithmic formula. If you don't know the logarithm, you must know the logarithm for algorithm course. So you can, there is one formula for logarithm that a raised to power log b. B is the base of log n, can be written as n raised to power log b a. Okay, so you can swap n and a here. Okay, you can swap these two in logarithm. So we will be swapping that one here. Okay, so this can be written as n raised to power 4 multiplied by n. We are swapping 32 and n. Log base to 32. And log base to 32 is actually 5. How come? So we can write log base to 32 as 2 raised to power 5. Okay, and this can be written as 5. We can take 5 here. 5 multiplied by log 2 raised to 2. And this is 1. This is 1. So it will be n raised to power 4 multiplied by n raised to power 5. Okay, so whenever two numbers are in multiply, their power can add. So it will be equal to n raised to power 9. So n raised to power 9 is actually equal to theta of n raised to power 9. So this is true. So these kind of question you can see in GATE examination. This is quite easy. So let's take one more example here. This is important. If Fn is equal to big O of Gn, then 2 raised to power Fn is equal to big O of 2 raised to power Gn. Okay, we need to find if it's true or false. If it's true or false. Okay. So how would you solve these kind of problems? You have already given that Fn, this is true. We are saying the question is saying that this is true. If this is true, then this is true or false. Okay. So how would you identify that? You can take some examples and try to put it in that way. Okay. So for example, we know that for example, we know that 2n is actually equal to order of n, right? Here this is Fn, this is Gn. Okay, this is order of n because 2n is less than equal to c multiplied by n, where c can be 2. You can put c3 here. Okay, so 2n is less than equal to 3n, right? So this is satisfied. We know that if this is satisfied, if we are taken this example, now how can we say that this is true or false? So if you try to put in 2 raised to, we have to put in this Fn and Gn in the power of 2. So let's say 2 raised to power 2n and 2 raised to power n. Are these two equal? Are these two here? Is this condition satisfied? Less than equal to Cgn. This is not satisfied actually. You can put any value of c. I will increase the value of n such that this condition fails. So this is a very good GATE question. It's a very good GATE question. You can check here that this is false. It is saying that if Fn equal to order of Gn, then 2 raised to power Fn is also equal to order of 2 raised to power Gn. So we have taken an example where 2n is actually equal to order of n, okay, where we can say that 2n is less than equal to cgn, and here, cn, and here we can put the value of c as 3. So 2n is less than equal to 3n, right? Now let's put this into the power of 2. So 2 raised to power 2n, could it be less than c 2 raised to power n? No, it can never be less than that. I will increase the value of n significantly such that you won't find a value of c which satisfies this condition. So this cannot hold. Remember this. 2 raised to power 2n is not equal to order of 2 raised to power n. Okay, remember this condition. There are many GATE and PSU questions which come around this thing. This is quite important. Okay. Now let's take few more examples, and this is also a good GATE question. Fn equal to n1 plus sine n. Like if you remember trigonometry, there are sine, cos were there. Okay, so this is that sine, and gn is equal to n. So can we say what is the relation between them? Is it Fn equal to order of Gn, or Fn equal to omega of Gn, or Fn equal to theta of Gn, or any kind of other relation can we state between these two? So let's say n Fn Gn. Let's put the value of n as 0, 90, 180, 270, 360, like this. Okay, so Fn is n raised to power 1 plus sine n, 1 plus sine n. Okay, so for 0, it will be, if you put value of n as 0, this will be 0. Okay, so 0. Gn will also be 0. For 90, it will be 90 square, because sine 90 is actually 1. Okay. For 180, it will be 180, because sine 180 is 0. So it will be n raised to power 1. Okay. For 270, it will be 1. Why? Because sine 270 is minus 1. If you remember, the value of sine theta or sine n will always vary between 1 and minus 1. Sorry, minus 1 and 1. Okay, it varies from minus 1 to 1. Okay, so what is the maximum value of Fn? What is the maximum value of Fn? It could be 1. What is the what is the minimum value of Fn, which is 1? Sorry, not 1, 0. In case of n equal to 0. What is the minimum value of Fn? 0. What is the maximum value of Fn? N square. From 0 to n square. It varies from 0 to n square. As you have seen that if you put value of n as 90, it will be 90 square. Okay, in case of 360, it will be 360, because sine 360 is actually 0. Okay, so value of Fn will be between 0 to n square. Sometimes it's 0, sometimes it's n square, sometimes it's 0, sometimes it's n square. Corresponding to that, Gn will always remain as n, 90, 180, 270, 360. So here you can see that the value of Gn is equal, smaller, equal, greater, equal. So here it's greater, here it's equal, here it's equal, here it's equal. So here it's smaller. So when you again go and try to put more values in n and try to find out any relation between these two, you won't be able to find any relation between these two, because the value of Fn varies from 0 to n. It could be 0, it could be n, it could be n square. So it goes like 0, n, or n square, or 1 also, sometimes 1 also. So 0, 1, n, n square, 0, 1, n, n square. Against that, the value of Gn will always be n. So how can you state the relation between these two? Because whenever the value of sometimes what happens that value will be 1 and Gn will be n only. Sorry, Gn will be n only. Okay. Sometimes the n plus sin n value will be n square and Gn will be n square only, because the sine function is periodic and its value changes from -1 to 1. Okay, so that's why we cannot state any relation between these two. As sine value changes from -1 to 1, the n1 plus the function n plus sine n will changes between 0 to n square. Okay, and Gn will always remain n. So sometimes the value of Gn will be greater than Fn, sometimes the value of Gn will be less than Fn. So you cannot state any relation between these two. Okay, so let's change the function a little bit. Let's take one more example. So whatever I am implying on sin n, the similar things will go for cos n also, because the value of cos n also changes between plus -1 to 1. Okay, the range of cos n or cos theta is -1 to 1. So if you say that Fn equal to 1 plus sin n, then Gn is equal to n square. Okay, so the maximum value of Fn is n square. It cannot go beyond Gn. So we can say that Fn equal to big O of Gn. Clear? Yeah. So you can replace sin n with cos n also. If you say that Fn equal to n1 plus cos n and Gn equal to n square, the relation stays same. The value of Fn lies between 0 to n square. The maximum value could be n square. Here, Gn is already maximum compared to Fn. Okay, so the relation is Fn equal to order of Gn. Okay. Yeah. So let's talk about some properties of asymptotic notation. Some properties of asymptotic notation. First one is reflexive. Reflexive means Fn equal to some notation Fn. So if notation is order, can it be true? Yeah, it can be true. Actually, it will always be true. Fn equal to order of Fn, so big O of Fn. So what is the case for omega? It will be true. We have seen the previous example, right? Where the both Fn and Gn were n square, and it holds for big O and omega. Okay, so reflexive property satisfies big O, omega, and theta also, because theta means that both functions are equivalent. Because in case of theta, we also saying that big O will also satisfy, omega will also satisfy, then only it is theta. So if these two are getting satisfied together, theta will also satisfy. So it's true for theta also. So what will be the case in case of small o and small omega? It will be false, right? Because these are strict boundaries. There is no equal to, right? So it will be false in this case. The next property would be, symmetric. So in case of symmetric, what happens? We are saying that if Fn equal to some notation Gn, then Gn equal to same notation Fn. So let's put big O here, big O here. If we are saying that Fn equal to order of Gn, this will also satisfy Gn equal to order of Gn. No, not necessarily, not necessarily. Not necessarily this is true. Because suppose if Fn equal to n and Gn equal to n square, this is true. So this is not true. Okay. So symmetric property is not satisfied in case of big O or omega, but it will be satisfied in case of it's false. False. It will be satisfied in case of theta. True. Because in theta, we are saying that both functions are actually equal. Okay. Both functions are actually equal. And it will be obviously false in case of omega, small omega and small o. False. So the next property would be transitive. Third one is transitive. Okay, so in case of transitive, we are saying that if Fn equal to order of Gn and Gn is equal to order of Hn, if this is true, then Fn is equal to order of Hn. Okay. So in this case, transitive property is true for all the notations. Transitive property is true for all the notations. It is true for big O, it is true for omega, it is true for theta, it is true for small omega, it is true for small o also. True. Okay. The next property is something that you have to remember, like there is no name for it. But if we are saying that Fn equal to order of Gn, and on the both side we append one more function, for example Hn, we append on the both side we append one more function, Hn dot Fn equal to order of Gn dot Hn. Will it hold? Yeah. This property is also true for all the notation, big O, omega, theta, small omega, small o. This is also true. So if this is true, we are assuming that this is true. So we can append same function on both sides. This will also be true. If this is true, then this will also be true. Okay. Now let's consider one more property. If we are saying that Fn equal to omega of Gn and there is one more function Dn equal to omega of En. So this is also true, this is also true. What can we say if we add these two? If we add these two, what can we say? If we add these two. Okay. So the first one is addition. Fn plus Dn will be equal to order of maximum of Gn comma En. Remember this. If you think logically, this holds. Okay. If you think logically that if you are adding these two, then on the right side we can take the maximum function. Okay. The second one is, what if we multiply these two? Fn dot Dn. Then on the right side also we have to multiply Gn dot En. Okay. If you are adding these two, I am specifically talking about big O notation only. Here I am specifically talking about big O notation only. If Fn equal to big O of Gn and Dn equal to big O of En, then summation of these two is equal to maximum of Gn comma En. and product of these two, product of left side equal to product of right side. Okay. Now let's consider the same property for omega, because these two are most popular. Same property for omega. Fn equal to omega of Gn and Dn equal to omega of En. So if we say Fn, we are adding Dn. Then in case of omega, we will take minimum of Gn, En. Minimum of these two. In case of addition. In the product, you can multiply. Fn or Dn equal to omega of Gn. Yeah. Because there is no lower bound. Omega means lower bound. Okay, omega means lower bound. Remember this, omega means lower bound. Okay, and big O means upper bound. Upper bound. Okay. Now let's solve a very interesting question on this one, and we are done with the asymptotic notation. Okay. So first we are given with some conditions. Then we have to give some statements on given expressions or equations. Okay. So first one is we are given that Fn equal to order of Gn and vice versa is not true. It is given, it is not true. Gn equal to, not equal to order of Fn. It is given. The second thing which is given is Gn is equal to order of Hn. And here the vice versa is also true. Hn equal to order of Gn. Okay, remember this. Fn equal to order of Gn and Gn is not equal to order of Fn. Here Gn is equal to order of Hn, and Hn is also equal to order of Gn. Okay, so both conditions are true. We are considering this is true. It is given. Now let's solve some of the expressions. First one is Hn equal to order of Fn. Is it true or false? Now you see that Hn is equal to order of Gn and Gn is not equal to order of Fn. So we can't apply transitivity here. If you remember the transitive rule, in transitive rule, if Fn equal to order of Gn and Gn equal to order of Hn, we can say that Fn equal to order of Hn. So using the transitive rule, we cannot apply transitive rule or any kind of rule here, any kind of property here to satisfy this condition. So this is false. If you think logically, this is already false because Hn is kind of equivalent to Gn because Hn is equal to order of Gn and Gn is equal to order of Hn. So these two are kind of equivalent. Sorry. Hn is kind of equivalent to Gn already, right? And Gn is not equal to order of Fn. So this is false. Second one is Fn plus Gn equal to order of Hn. Yeah. Okay. So here if you see that Fn plus Gn, in case of Fn plus Gn, Gn is kind of greater. Gn is kind of greater. Yeah. You can see that Fn is equal to order of Gn. Okay. And Gn is not equal to order of Fn. So Gn is already kind of greater. If you remember the condition that if Fn is equal to order of Gn, then Fn is less than equal to Cgn. So Gn is kind of greater or equal, always greater or equal. Okay. So this condition already holds. This condition already holds. Okay. So based on this condition that Gn equal to order of Hn, we can say that if we add these two, whenever addition happens, the more effective one can be taken. For example, as you have seen in the previous example, n square plus n can be written as order of n square, right? Can be written as order of n square. N4 plus n cube plus n square can be written as order of n4. Okay, so in case of multiple terms, the most weighted terms will be considered for asymptotic notation. So here the most weighted terms is Gn. Using this reference, you can say that Fn is less than Cgn. So Cgn is more weighted compared to Gn, and Gn is equal to order of Hn. So this is true. Okay, the third one is Gn dot Hn equal to order of Fn dot Hn. Right? So this is obviously false, because here the weight of Gn is, if you remove these using this rule, okay, where if this condition satisfied, we can append function on the both sides. So we can remove also. We can remove the same function on the both sides. If you remove this function, this is already given that this is not equal. Okay, so this is false. Gn dot Hn equal to theta of, sorry, not theta, big O of Hn dot Hn. Okay, so let's remove the same term both sides. So Gn equal to order of Hn, it is already given. So this is also true. So this one is false, this one is true, this one is false, this one is true, this one is false, this one is true. So in ABCD, B and D are true. A and C are false. So this is more than enough for gate examination, considering asymptotic notation. Okay. So asymptotic notation and analysis are connected. So once you know the asymptotic notation for a given code snippet, you can identify the time complexity and you can denote them in form of asymptotic notations. Okay. So let's move on to another topic, which is recursion. Okay. So what is recursion? Recursion is like calling same function, calling a function in itself. So why would anybody wants to do that? Right? If you are given with an input of size n, okay, you want to reduce the input size to solve the problem. So once the input space is reduced, the problem is also reduced. Suppose you are given an array of size 100. Okay, so you want to call the same function again with reduced size of 99. You have eliminated one element, right? So the input space is reduced, and we are calling the same function on remaining input. So that's why recursion can be used. In recursion, always remember the input space will always be reduced once we call the function. For example, if we take factorial. So if we take factorial of 4, what is factorial of 4? 5 multiplied by 3 multiplied by 2 multiplied by 1, right? So can we denote this factorial in a recursive manner? Yeah, we can. Factorial 4 can be written as 4 multiplied by factorial 3. And factorial 3 can be denoted as 3 multiplied by factorial 2. And factorial 2 can be written as 2 multiplied by factorial 1. And factorial 1 can return 1. 2 multiplied by this. Okay, so once 1 is returned, 2 multiplied by 1 will be returned here. So it will be 3 multiplied by 2. And 3 multiplied by 2 will be returned here. And this will be the same thing. So you see, initially the input space is 4. And we reduce this size by 1, 3. Then we reduce this size by 2. After multiplying with 3, we call 2. So this function will be called and the factorial will be calculated once it goes back, once it returned. So this arrow shows calling and this arrow shows returning. So I'll be explaining how returning happened and how calling happened in the upcoming in this lecture only. But let's focus on this factorial problem. So for a given number n, what can you say? How can I calculate the factorial? Okay, I have a function. I have a function FACT. I passed n. So I can simply say if in this function I can write if n equal 1, return 1, else return n multiplied by factorial of n minus 1, and we are done with the problem factorial. So this every recursive, remember, every recursive solution can be converted into iterative solution. Iterative solution, which contains like for loop or while loop, right? Every recursive solution. But sometimes recursive are more beneficial compared to iterative solutions because if you write for loop here, okay, it looks more like compact code. But in case of particularly factorial, iterative solutions are better because let me tell you why. Okay, so what happens whenever a function gets called? It will create a stack. You have seen the stack overflow problem. Why that happens? Because one function call another function. Sometimes that another function is that function itself. Okay. So for example, what happens? The A will call B and B calls A. So this goes on and stack get overflowed. So whenever this is the stack, in your memory, stack plays very important role. So initially, I call A. I say that let's call A. A will be called, right? Then A called B. It pushed the call of B in this stack. Okay. Then B called A, and this happens. And stack have limited memory, a finite memory. After some 1,000, that depends upon the computer memory. After some 1,000 or 20,000 iterations, it will throw us an error. That stack got overflowed. So why do the programming language create stack at the first? Why did they create this stack? Because using this stack, they can track the return time. Okay, so let's talk about the factorial problem again. This factorial problem again. Okay. Remember this program. For this program, where if n is equal to 1, we will return 1. If it's not 1, it will return n multiplied by n minus 1. Later on, this n minus 1 will be here, and it will be n minus 1 multiplied by factorial n minus 2. Okay, I hope you get that. So let's create a stack for n equal to 5. Okay, it will save that 5 multiplied by factorial. I am representing factorial as f of 4. Okay, then for f of 4, 4 multiplied by f of 3 will be called. Right now, we are calling and saving it in stack. It haven't returned any value till now. 3 multiplied by f of 2. 2 multiplied by f of 1. Now, in case of f of 1, will return 1 here. 1 will be returned here. Okay, 1. Here, 2 multiplied by 1 will be returned. Here it will return 3 multiplied by 2 multiplied by 1. Here this will return 4 multiplied by 5, sorry, 3 multiplied by 2 multiplied by 1. Here the whole process will return. Whenever the function returns, this will delete the entry from stack. Whenever the function returns, this will delete the entry from stack. So in case of recursive function or any kind of function call, we save the instance of that function into stack, okay, so that we know when this function is going to return. Whenever this function is calling another function, it could be the same function or another function, it will be saved on the top of this current function, right? So that we know that this function is called, this function is called after this one. Using stack, we can track that, right? We know that whoever have called in the last will return first, right? So this is this policy will be followed. Whoever pushed the last will be returned first. Okay, so using stack we can track that. So if we haven't introduced this base condition here, n equal 0, what happens that it will keep on calling like f0, f minus 1, it will keep on calling. And stack of limited finite memory, we will get stack overflow error. So we have to be careful that this is called base condition. This is must in case of recursion or any kind of function calls. Okay. So this is quite easy that I hope you understand what is recursion. Using recursion right now, we have solved the factorial problem. You can see this example. Okay. So let's take one more example of the recursion, which is basically Fibonacci series. So you know that Fibonacci series is 0, 1, 1. Okay, initially it's 0 and 1 only. Then we will add these two, and the next number is 1. Then we will add these two. The next number is 2. Then we will add these two. The next number will be 3. We'll add these two. It will be 5. We'll add these two. It will be 8. We'll add these two. It will be 13. Like this, it will go on. Okay. So this is the Fibonacci series. How can we generate a Fibonacci series of a given size? For example, if we are given that we have to print a Fibonacci series of n size. Okay, n size. We are not considering 0 here. The n size is this one: 1, 2, 3, 4. For example, if n is equal to 5, we say that 1, 2, 3, 4, 5. Okay. So this will be the Fibonacci series: 0, 1, 1, 2, 3, 5. Can we solve this using recursion? Yes, we can. If you remember that from this point, the base condition is if n is equal to 0, return 0. If n is equal to 1, return 1. Okay. Else what will happen? We will return Fibonacci of n minus 1 plus Fibonacci of n minus 2. You can give them index like this. This is 0 index, this is 1 index, this is 2, 3, 4, and 5. So for second index, what I'm doing, I'm adding first index first index value plus 0th index value. Okay, I'm adding these two. For third index, I am adding second index value plus first index value. Okay, so if this is n, I am adding n minus 1th index and n minus second index. Okay, if this is n, I am adding n minus 1 and n minus 2 index value. Okay, so this is the base condition. And this is Fibonacci function. I will run it like this. I will have Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay, let's create a tree-like structure for this call. Okay, so if I call Fibonacci of 6, what will happen? Fibonacci is 6. So 6 is not 0 or 1. I'll be calling Fibonacci of n minus 1 and n minus 2, which is Fibonacci of 5 and Fibonacci of 4. Okay, and for Fibonacci of 5, I will be calling Fibonacci of 4 and Fibonacci of 3. And for the Fibonacci of 4, I will be calling Fibonacci of 3 and Fibonacci of 2. For 4, I will be calling Fibonacci of 3 and Fibonacci of 2. For 3, I will be calling Fibonacci of 2 and Fibonacci of 1. For this, I will be calling Fibonacci of 2 and Fibonacci of 1. For this, I will be calling Fibonacci of 1 and Fibonacci of 0. For this, I will be calling Fibonacci of 2, Fibonacci of 1, Fibonacci of 1, Fibonacci of 0, Fibonacci of 1, Fibonacci of 0, Fibonacci of 1, Fibonacci of 0. Because we have added base condition for 1 and 0, we won't be calling further functions. For 1, we will be returning for 2 also, Fibonacci of 1 and Fibonacci of 0. For 1, we will be returning 1. For 0, we will be returning 0. Okay. So this is the call structure. This is the calling tree. This is how the tree will be called. Now remember, what is the call sequence? Sometime GATE asks you, or any other important exam may ask you, what is the calling structure? In which order these functions have been called? Okay. In which order these functions have been called? So let me tell you one important thing here. You should make a note of it that always in recursion, the calling happens. I should add it here. Note. In recursion, calling happens pre-order. Tree pre-order, okay, tree pre-order. And returning happens post-order. Okay, so let's see. What is the pre-order? First this one, then this one will be called, then this one will be called, third, fourth, fifth, sixth. Okay, then this one will be called seventh. What is pre-order? Root, left, right. This is pre-order. What is post-order? Post-order, it's left, right, root. Okay. So then this one will be called, then this one, 8, 9, 10, 11, like this. So here, this is 12, 13, 14, 15, 16, 17. At the 17th position, this will be called. 18, 19, 20, 21, 22, 23, 24, and 25. Okay, but how the function will be returned? It will be post order. Left one is this one. This is the leftmost. But this will be called. Okay, so let me mark them with green color. First, this one will be called. Then left, right, then root. Okay, then this one will be returned. First, this function will return the value. This function will return the value. Then addition will happen here, and this one return the value. This one will return the value. Okay. Now then this one will return the value 4, and addition will happen here, and this one will return the value. Okay. Now this one will return the value 6th, 7th. Then both will return the value 8th. This one will return the value. At the 9th position, this one return the value. This is how post order will be executed. So remember, the calling of the functions, recursive function happens pre-order wise, and the returning of the function happens post-order wise. So this is the order of the return. This is very important question asked in many of the examination of computer science, that in which order the function is called and in which order the function are returned. Okay, so this is one important question. Another one is, what is the time complexity of this Fibonacci? If we execute this recursion function of Fibonacci, this recursion function, okay, this is the base condition, and we are running it like this. What is the time complexity? We can calculate the time complexity in this tree. So the height of tree is actually the height of tree. This height of tree actually can grow to n. Okay, so we have n levels. You can see here the maximum level is the leftmost one. This is the leftmost one level. 6, 5, 4, 3, 2, 1. Okay, so we have n levels. It can go, its depth is n. Okay, so how many node of n level? A complete bandity. It is almost complete bandity. This is called almost complete bandity. Okay, so let's see what happens in case of complete. We are considering in time complexity, we always consider worst case time complexity. Okay, which could happen in worst case. I hope you have noted down this note. This is quite important. Then let's consider a binary tree. Binary tree can have 2 nodes, right? So let's consider a complete binary tree. So this is what, how many levels are there? 3 levels, 1, 2, and 3. How many nodes are there? 2 raised to power 3 minus 1, which is 7. 1, 2, 3, 4, 5, 6, and 7. Okay. So let's consider one more level. You can count the nodes. If you have 4 levels, we'll have 2 raised to power 4 minus 1. If you have n levels, we will have 2 raised to power n minus 1 nodes in the tree. Okay. So given this Fibonacci tree, almost complete, we will consider the worst case time complexity, which is almost around 2 raised to power n minus 1. We will have 2 raised to power n minus 1 nodes in this tree, and each node will take at least constant time, right? At least there is one addition happening, at least constant time. So what is the execution time of this whole tree, this Fibonacci n, fn? What is the time complexity of fn? Fibonacci of n. What is the time complexity? This tree can show you that these many calls are happening, these many functions are executing, and each function is taking at least one addition. Okay, one addition, doing one addition, right? So 2 raised to power n minus 1 is the effort effort for Fibonacci n. So the time complexity is order of 2 raised to power n for this algorithm. It can be improved using dynamic programming, but we will see that in dynamic programming. Okay. Can be improved using dynamic programming. So that we will cover in dynamic programming part. So the time complexity will be order of 2 raised to power n, which is quite high, very high. This is exponential. It is very high. So we can reduce it using dynamic programming. Okay. Similarly, we can have more recursive function like GCD. Okay, GCD. So if we have two numbers like n and m, the GCD can be calculated using one recursive relation, very simple one recursive relation. If n is equal to 0, the answer is m. If m is equal to 0, the answer is n. Okay. Else the answer is GCD of n remainder by, m remainder by n, comma n. Okay. You can see the recursive function of GCD and you can check the time complexity. So this is the recursive function. Okay. You will take the remainder here, like m remainder by n and n here. Okay. So that's it for today. Thank you all for watching this lecture. I hope this helps you better to understand algorithm part. So once you know the recursive function and how you can calculate the time complexity of this recursive function. So right now here, we have calculated the time complexity as order of 2 raised to power n by constructing this tree. Okay. So this method of calculating time complexity by constructing this tree called recursive tree method. So there are three methods for calculating time complexity of recursive relation or method. These are called recursive relation. Okay. The time complexity of recursive relation can be calculated using substitution method. Second one is recursive tree method. And third one is master method. Master method have master theorem. So I'll be explaining master theorem to you. And recursive tree method you have already seen that this is recursive tree method. You will actually try to implement or get an idea of level of the tree and number of nodes in the tree and each effort of each node. Okay, effort of each node. Once you have these three things, the depth of the tree, number of nodes in the tree, and the effort at each node, you can calculate the time complexity. Here, effort is constant. You can consider it as 1. So we have 2 raised to power, almost 2 raised to power n nodes. So time complexity is order of 2 raised to power n. Okay. And the easiest one is master method, but this is not applicable to all the recursive relations. This is quite straightforward, but this is not applicable to all the recursive relations. And the most important one is substitution method. Mostly in examination, you see question around master method. You will be given a recursive relation. For example, something like t raised to power n equal to, if n equal to 0, return 1, else t raised to power 2 into t raised to power n by 2 plus 1, something like this. You see recursive relation in this format. Okay, and you can convert this Fibonacci into that format only. So let's convert this standard format for recursive relation. Okay, so what was our function? Recursive function. The function was return 0 if n equal to 0, if n equal to 1, return 1, else Fibonacci of n minus 1, else plus Fibonacci of n plus 2. Sorry, n minus 2. Okay. So we can convert this into t raised to power tn equal to where n is the input, like here the Fibonacci number, and you can return 0 if n equal to 0, you can return 1 if n equal to 1, else you can say that tn minus 1 plus tn minus 2. Okay, you can return this function into the standard format. And using substitution method also, we will try to calculate the time for this one. And we will first take more easier example, then we will move on to this example. Okay, so that's it for today. Thank you for all joining.